Welcome to the deep dive. Today, one of our listeners sent us down a really interesting path, looking at some, well, let's call them high-performance 3D printing filaments.
Yeah, we're moving beyond the basic stuff here. We're talking carbon fiber PLA, that's PLA-CF, and also metal PLA.
Right, composites.
Mm-hmm.
Not just for prototypes anymore. These are for, like, actual functional parts, or
Yeah.
really high-end looking objects.
Exactly. And our mission today really is to dig into what it actually takes to use them. The sources we looked at make it clear it's not just buying the spool.
What else is involved?
Well, there's the performance, the pros and cons, obviously. But the big thing is the hardware you need, the specific print settings, maybe even post-processing work. There's a hidden cost of entry, you know?
Okay, that makes sense. And these two are kind of opposites, aren't they?
Mm-hmm.
PLA-CF aiming for strong and light,
Performance-driven.
while metal PLA is all about weight and looking, well, metallic, almost purely aesthetic.
Pretty much. One's about function, the other's about feel and finish. Big difference.
Okay, let's unpack this. Where should we start? Maybe with the performance one.
Sounds good. Let's dive into carbon fiber PLA, the PLA-CF.
Right, so fundamentally, it's just PLA plastic, the stuff most people start with, but mixed with tiny bits of carbon fiber.
Yeah, short, chopped carbon fibers. And they make a huge difference. The sources all agree this isn't just a minor tweak. It dramatically boosts stiffness and strength. We're talking about the elastic modulus going way up.
Stiffness meaning it doesn't bend easily under load.
Exactly. Perfect for parts that absolutely have to hold their shape. Think mechanical components, things under stress.
Like what sort of things are we talking about application-wise?
Well, the sources mention things like jigs and fixtures for workshops, which makes sense, but also lighter weight stuff where strength still matters. Drone frames, RC car parts, maybe lightweight brackets, anywhere that strength-to-weight ratio is critical.
And dimensional stability, that sounds important too. Less warping.
Huge benefit. Those fibers basically act like a skeleton inside the plastic, stopping it from shrinking so much as it cools.
Ah, okay. So you get really precise prints, good for parts that need to fit together perfectly.
Definitely. Minimal warping is a big plus with this stuff. And, it looks pretty cool, too.
Oh, yeah. How so?
It prints with this really nice matte black finish, kind of textured. And that texture does a great job hiding the layer lines you usually see with FDM prints.
So less sanding just to make it look good.
Right. For functional parts, often it looks great straight off the printer.
Okay, this sounds amazing. Strong, stable, looks good. What's the catch? Because there's always a catch.
Yeah, there definitely is. First off, price. This stuff isn't cheap. We're talking like significantly more expensive than your standard PLA roll. Premium material, premium price.
Okay, cost. What else? You mentioned handling challenges earlier.
Yes, the filament itself. While the printed part is strong, the raw filament on the spool is actually quite brittle. Those fibers make it stiff, but also easy to snap.
Ah, so you need to be careful feeding it into the printer.
Very careful. You need a smooth filament path, no sharp bends. If the spool gets snagged or the path is too tight, it can just break mid-print.
Does that mean things like humidity are a bigger problem too? Does it get even more brittle if it absorbs moisture?
Good question. Yes, moisture definitely makes the brittleness worse. Pure PLA can handle a bit, but these composites, much liver forgiving. You really want a good direct feed system and ideally keep the filament stored dry, like in a dry box, maybe even one that's heated.
Okay, so careful handling, dry storage.
Yeah.
Anything else on the downside for PLA-CF?
One really important point, health and safety.
Ooh.
If you sand it, and you might want to for smoothing functional parts, you absolutely need respiratory protection, a good mask.
Why? Just because it's dust?
Not just any dust, carbon fiber dust. The sources specifically warn that inhaling it is harmful to your lungs.
Right.
It's not like sanding regular plastic. You got to take it seriously.
Right. Good warning. Okay, so that's PLA-CF. Strong, light, stable, looks good, but expensive, brittle filament, and you need a mask for sanding.
That's a pretty good summary.
Now, let's shift gears completely. Over to metal PLA.
Yeah, the aesthetic powerhouse.
Forget lightweight here, right?
Yeah.
This is all about making things feel heavy and, well, metallic.
Totally. It's usually a PLA base again, but it's loaded, and I mean loaded, with fine metal powder. Iron, bronze, copper, stainless steel. Sometimes over 60% of the weight is just metal powder.
60%, wow. So the whole point is that heavy, cool-to-the-touch feel.
Exactly. You pick up a part printed with this, and it feels substantial, like real metal, in a way plain plastic just can't.
Does it look like metal right off the printer?
See, that's the interesting part. Nope, not at all, actually.
Really? What does it look like then?
It comes out looking kind of dull, matte, almost like stone or ceramic, maybe a bit sparkly depending on the light, but definitely not shiny metal.
Why is that? If it's full of metal powder.
Because the metal particles are encased in that thin layer of plastic binder right on the surface. The plastic hides the metal.
So, you have to get rid of that plastic layer somehow.
Precisely. Post-processing isn't just an option with metal PLA, it's basically mandatory if you want that actual metallic look. The real work starts after printing.
Okay, walk me through that. How do you get the metal to show?
It's a process, and it takes effort. Step one is removing that surface plastic, usually mechanically.
Like sanding.
Yep.
Hmm.
Starting with coarse sandpaper, maybe 100, 200 grit, something like that. Or you could use a wire brush, carefully. For lots of small parts, some people even use a rock tumbler with abrasive stuff inside.
Okay, so you grind off the plastic skin. Then what?
Then comes the polishing. Lots and lots of polishing. You move to finer and finer grits of sandpaper.
How fine are we talking?
The sources mention going way up, like maybe even up to 12,000 grit if you're aiming for a real mirror finish. Then maybe even buffing with polishing compounds, perhaps with a Dremel or something.
12,000 grit. Wow, okay. That sounds intensive. Like, are we talking hours of work for one part?
Oh, easily.
Yeah.
The sources imply this isn't a quick job. It's a real commitment if you want that super polished, authentic metal look. It's definitely a labor of love.
So you sand, you polish. What else can you do?
Well, this is where it gets really cool, I think. You can do patination, artificial aging.
Like make it look old and weathered.
Exactly. You can accelerate rusting on iron-filled PLA using something simple like salt water. Or for copper and bronze filaments, you can force that greenish-blue patina, the verdigris, using things like vinegar, salt, maybe some hydrogen peroxide.
That's amazing. You're basically creating controlled corrosion for an artistic effect.
Pretty much. It lets you get really authentic-looking antique finishes.
Okay, so after all that sanding, polishing, maybe aging, are you done?
Almost. One final recommended step is to seal it. Coat the finished part with a clear varnish or lacquer.
Why seal it? To protect all that hard work.
Exactly. It protects the finish you just spent hours creating, it stops fingerprints from messing up a high polish, and it prevents further unwanted oxidation or tarnishing, because remember, that metal powder is now exposed on the surface.
Right, makes sense. So drawbacks for metal PLA,
Right.
also expensive.
Yep. And the spools are often smaller or lighter, like 750 gram instead of 1 kilogram, because the material itself is so dense, you pay more for less filament length.
And it's also brittle as a filament.
Yes, just like the PLA-CF, that high filler content makes the filament itself prone to snapping. It needs careful handling and a good feed path.
Okay, so we've got PLA-CF for strength and metal PLA for looks and weight. But you mentioned something they both share, a big technical hurdle.
Yes, and this is probably the single most important takeaway from all the sources, connecting the dots here. Both of these materials, because they're filled with hard stuff, carbon fibers or metal powder, share one critical problem. They're extremely abrasive.
Abrasive, like sandpaper.
Exactly like sandpaper, but flowing through your printer's hot end. The sources are really clear on this. Metal particles, in particular, are described as some of the most abrasive things you can possibly print with in FDM.
So, what does that mean for your printer? You can't just use a standard setup.
Absolutely not. Forget it. You cannot just load the stuff into a standard printer with a typical brass nozzle and expect it to work.
Why not? What happens?
The sources are unanimous and very direct. You must use a hardened steel nozzle. It's not a suggestion. It's an absolute requirement for both PLA-CF and especially metal PLA.
What happens if you ignore that? Say you try metal PLA with a cheap brass nozzle.
Disaster. The metal particles will just grind away the soft brass. The sources say a brass nozzle can be destroyed, like completely ruined incredibly quickly, sometimes in just a few minutes of printing.
It's serious.
Seriously. The nozzle hole widens out, you lose all precision, your extrusion becomes a mess, the nozzle is just toast.
Wow. Okay, so step one is buying a hardened steel nozzle. That's an extra cost right away.
Yep. Non-negotiable hardware upgrade.
What else? Does the abrasiveness cause other problems, like clogging?
It can contribute, yeah. Clogging is generally more common with filled filaments anyway, just because there's stuff in the plastic. To help prevent that, a larger nozzle diameter is strongly recommended.
Bigger than the standard 0.4 millimeter.
Definitely. For PLA-CF, the advice is usually 0.5 millimeter or 0.6 millimeters. For metal PLA, because those particles can be chunky, 0.6 millimeters, or maybe even larger, like 0.8 millimeters is often better. Just gives the particles more room to get through.
But wait, using a steel nozzle, Doesn't steel conduct heat differently than brass?
It does. That's another complication. Steel has lower thermal conductivity than brass.
Meaning it doesn't transfer heat to the filament as efficiently at the very tip.
Exactly. So you often need to compensate by increasing your printing temperature, maybe 5 or 10 degrees Celsius higher than you'd use for the same plastic with a brass nozzle.
So for PLA-CF, instead of maybe 210 degrees C, you might need 215 degrees C or 220 degrees, maybe even up to 230 degrees C.
Yeah, something in that range, typically 200 to 230 degrees C. You need that extra heat to make sure the filament melts properly right at the nozzle tip, despite the steel being less conductive.
Okay, steel nozzle, bigger diameter, higher temp. Any other settings to watch out for?
Retraction. This one seems a bit weird, but it's important.
Retraction, pulling the filament back to prevent stringing. You need to change that.
Yeah, you generally need to reduce retraction, both the distance it pulls back and the speed it does it at.
But why? Doesn't that mean more stringing?
It might mean slightly more stringing, yeah. But the problem is, with these filled filaments, retracting too much or too fast can cause the solid particles, the fibers, or the metal powder to jam up in the cold end of your hode end, above the melt zone.
Ah, creating a plug.
Exactly. The sources cite this filler accumulation during retraction as a really common cause of clogs that are hard or impossible to clear. So you dial back the retraction to keep things flowing smoothly, even if it means a tiny bit more cleanup later. Reliability over perfect stringing control.
Got it. Trade-off. And with metal PLA being so abrasive, does it wear out anything else besides the nozzle?
It can, yes. One other part to watch is the extruder drive gear, the little gear wheel with teeth that grips the filament and pushes it.
Oh, right, the feeder wheel.
Yeah. If that gear isn't made of hardened steel itself, the constant grinding of the metal filament passing over it can actually wear down the teeth over time.
Wow. So metal PLA really demands a robust, almost industrial-grade pathway. Hardened nozzle, hardened feeder
There's
gear.
so much, it's demanding stuff.
Okay, so let's quick and summarize the choice for the listener, if you're trying to decide between these two.
It comes down to your primary goal, right? And accepting the required upgrades and effort.
If you need parts that are strong, stiff, dimensionally accurate, and relatively light, like functional brackets, jigs, drone parts, you go for PLA-CF.
Yep. And you accept the cost, the brittle filament that needs care, the need for a hardened nozzle, maybe a bigger diameter, and the safety precautions if you sand it.
But if what you want is that unique feel, the weight, the cold touch, the authentic look of metal, maybe for display pieces, props, high-end enclosures,
Then metal PLA is your choice, but you go in knowing it's expensive, the filament is brittle, you absolutely need that hardened nozzle, probably 0.6 millimeters or larger, maybe hardened extruder gears.
and crucially, you're signing up for potentially hours of post-processing.
Yeah.
Sanding, polishing, maybe patination, then sealing.
That's the deal. The print is just the starting point for metal PLA. The real result comes from the finishing work.
Now, connecting this to the bigger picture, there's one more shared aspect we haven't touched on much, the environmental side.
Yes, the end-of-life issue. That's a really important point for composites like these.
Unlike pure PLA, which can sometimes be industrially composted, these filled materials, they're different, right?
Completely different. Because they contain carbon fiber or metal powder mixed right in, they can't be recycled through standard plastic recycling streams, and they're definitely not compostable.
So what happens to them? Where do they go?
Mixed waste, unfortunately. Landfill or incineration, depending on local facilities. There's currently no mainstream way to separate the plastic from the filler effectively for recycling.
That definitely adds something to consider, doesn't it? Maybe reserving these materials for parts that are truly necessary or will have a long lifespan given their end-of-life impact.
It does raise that question of responsible use, for sure, especially given the higher cost and energy involved in making them in the first place.
Okay, so that brings us to a final thought. We've seen PLA-CF offers huge functional improvements over basic PLA, and metal PLA offers a completely unique aesthetic and feel.
Yeah, specialized materials for specialized jobs.
So here's the provocative question, maybe. Given how much better PLA-CF is for structural parts,
Right.
and how unique metal PLA is for certain looks, how long can regular unfilled PLA really stay the default go-to filament?
That's interesting. You're asking if the future is specialized composites.
Well, yeah. Despite the higher cost, despite the need for hardware upgrades, if you're serious about functional printing or high-end aesthetics, are these advanced materials eventually going to push basic PLA aside for anything beyond simple prototypes or toys?
That's a good question. The barrier to entry, the cost, the hardware, the learning curve is still significant. But the performance and aesthetic gains are undeniable. It really makes you wonder if overcoming those hurdles is just becoming part of the evolution of FDM printing for anyone who wants to move beyond the basics.
Food for thought. It seems the path to better prints might just lie in mastering these more complex, more demanding, but ultimately more capable composite materials.